climate change. And with that, I'm going to turn it over to our introductory speaker, Dr. Cynthia West, who is the Executive Director for the Office of Sustainability and Climate Change. Welcome, Cindy.
Thank you, Bill. Appreciate the setup and getting us started here on time. And I want to welcome all of you who are joining us today to learn more about long-term drought and potential water challenges that we will be facing in the future. Concerns over long-term drought effects in the United States have been growing as climate projections of hotter and drier conditions in some areas of the country are being realized. Many of you have witnessed the devastating effects of drought on the landscape and experienced those serious threats posed to the resilience and security of communities, our forests, and grasslands nationwide. Nowhere else is the impact of long-term severe drought felt more than in California, where an estimated 66 million trees have died in a 6-county region in central and southern Sierra from multiple years of drought, stress, and bark beetles. The impacts of climate change are expected to increase the frequency, intensity, and duration of droughts in many regions, and thereby increasing vulnerabilities and in some places causing significant foundational changes to the land and those ecological services that flow from our forests and grasslands. Not only by understanding our current and future vulnerabilities of forests and grasslands from climate-driven long-term drought, can we hope to develop strategies and tactics to reduce the impacts from these events, or in some cases to recover. In fact, federal agencies have been called upon to work together in ways that we've not been challenged in the past to pool our knowledge, our authorities, our resources to address the impacts to the nation from drought. In March of this year, President Obama announced the development of an interagency National Drought Resilience Partnership, co-chaired by Usda and NOAA. The partnership released a long-term drought resilience federal action plan, and it includes 2 actions that address forests and federal lands. They are to examine and understand the ecological impacts of drought across the United States on our forests and grasslands, and to manage our federal assets to promote local drought resilience from these impacts. This webinar is just the start for us in our Forest Service and working with our partners in trying to deliver our programs to protect communities from fire, increase resiliency on the landscape, deliver services from our forests and grasslands. And so for us, it is to get a clarity and a focus to understand the vulnerabilities to forests and grasslands from drought through this kickoff and through focused regional workshops with managers over the next year. We must develop a better understanding of the risks and vulnerabilities to our key resources from long-term drought. So today we start to to increase our understanding of drought impacts on ecosystems, to better inform our efforts to address risks that are intersecting with drought, wildfire, insects and disease, invasive species in drought-prone regions. Our current projections of climate change indicate increased wildfire potential, especially in areas impacted by prolonged drought. These workshops that we plan to hold over the next year with a regional focus will help us develop a set of local strategies and tactics to reduce, mitigate, or in some cases recover from the impacts of drought, and to gain a better understanding of the trade-offs of our actions to provide for those things that are being asked of us from our forests: carbon sequestration, water stewardship, critical habitat, and recreation services. The Forest Service Office of Sustainability and Climate Change, along with the climate hubs, are working with our regional offices and partners to convene regional workshops over the next year, as I mentioned. These are to help us better prepare for drought impacts ahead of another emergency as we're facing in California. I like to say it's doing the sense-making of what we're about to hear and learning more about the local challenges, conditions, and opportunities to address drought or to mitigate risk. A recent synthesis of wildfire and drought published by the Forest Service titled Drought Impacts of U.S. Forest and Rangelands, a comprehensive science synthesis, acknowledges droughts increasing and contributions to risk of wildfire occurrence and impacts. Our understanding of the relationships between drought and fire severity and the extent the impacts on future vegetation, carbon sequestration, and water quality is limited. And you will hear more about that today and how we are trying to fill our knowledge gaps. Restoring forested ecosystems and increasing resilience to these landscapes to climate change is a high priority for federal land managers, and in particular for the Forest Service. So today you will learn more about the intersection of the impacts of long-term drought on our activities to reduce fire risk, to steward water, to provide high-quality recreation services, to manage across our forest and range vegetation. And you will hear about how not only are our actions and our potential actions affecting the landscapes, but to gain a better comprehensive understanding of those things that we must do with our operations and in managing our own infrastructure that we can change to reduce our consumption and our impact on water resources. Previously, the Forest Service initiated climate vulnerability assessments and adaptation planning across our regions and reported our progress through a climate scorecard. Now, to meet the National Drought Resilience Partnership goals, we are implementing these series of regional workshops and hope that you will be able to join us in those. The importance of working together toward meaningful actions on the ground based on the best available science is critical to our mission. And I ask that you and your partners and your peers provide support to our regional workshops that will be coming up. And let's get started launching our journey together on understanding the impacts and implications of long-term drought to our forests and rangelands. Thank you.
Thank you, Cindy. Thank you very much. Just a couple of quick responses to some of the chat coming in. There was just that one intro slide, and so those of you that were worried that we weren't advancing any slides, we're good to go. I think the audio is okay. Let us know if there's any problems with the audio, and we'll work on that PIN number for the phone call in. But again, we're hoping that everybody will just go ahead and type their information in the chat window, any kinds of questions. So we're going to move on here. Dr. James Vose with the USDA Forest Service Southern Research Station. James is a research ecologist and project leader of the USDA Forest Service Southern Research Station, Center for Integrated Forest Science at North Carolina State University in Raleigh. Prior to this current appointment as project leader of CIFS, he spent 25 years at the Coweta Hydrologic Lab studying watershed ecosystem responses to disturbances in forest management. More recently, he has led numerous regional and national syntheses of ecosystem responses to climate change and drought. Dr. Vose, welcome. Look forward to your presentation.
Great. Thank you, Bill. So what I'd like to do in my 15 minutes or so is build a little bit on the introductory comments from Cindy West, but also provide a little bit of a foundation for the talks that you'll hear after my presentation. And what I'd like to do is give you just a brief overview of the drought science synthesis that Cindy mentioned. And it is a series of reports and science papers that really form the scientific foundation for the work to come, essentially translating the science into management actions. I was one of several folks who led the effort. Jim Clark, Charles Luce, and Toral Patel-Wainen were co-leads, but we had significant contributions from several of our colleagues in universities, other federal agencies, and national labs. And so, again, I'd like to just sort of give you a brief overview of that, a little bit about the motivation, a little bit of purpose, and provide some context for the talks that you'll hear a little bit later some of which are being delivered by co-authors on the report or others that actually use information from the report itself. So as I mentioned, it was a general technical report that is published. It's in the literature now. You can get this from the Forest Service or contact me if you'd like a copy of it. We addressed several topics in great detail. And these were 30 or 40 page, very detailed science synthesis where we identified the ecosystem or socioeconomic or hydrologic effects, whatever the particular topic was, identified shortcomings and needs and challenges, but really didn't delve deeply into the next phase, which is so important now, and that's how do we translate this science into management responses. We also published the subset of the papers in some special issues of some pretty substantial scientific journals. And again, you see the citations there. You can contact me if you'd like copies of the papers themselves, or just go to the journal or Forest Service websites and you can get these individual papers as well. So I guess the bottom line is that over about a 2-year period, myself and colleagues and experts from across the country did this very extensive, very deep science synthesis, which is so critical for moving forward in response. So as Cindy mentions, we are all experiencing the impacts of drought. They're in the news. This is not an event that is necessarily local or hidden or only a few people know about it. The widespread forest mortality, the substantial increased cost of fighting fires, and the threats of water scarcity in places running out of water are certainly portend both an existing risk or threat to forest health, but if these drought impacts continue or worsen in the future, these issues will only get more substantial and only create even greater challenges for forest management. So we actually began the synthesis while these events were in play, and they continue and will likely continue into the future. So what was the motivation for the synthesis? Well, as mentioned, there has been this recent widespread drought, and although it's difficult to predict drought into the future, and I'll address this here a little bit, there is certainly strong evidence that climate change related forces will make droughts get worse in the future. Forest and rangeland responses differ significantly from agriculture. A lot of the perspectives by the public about drought is very driven by agriculture, where you might have a drought that's particularly bad, but next year it rains and you can plant a new crop and grow again. Well, forest effects are much longer lasting and take much longer to recover from, and it can set forest dynamics and ecosystem effects on a trajectory that may take decades or even centuries to recover from. And so having a science synthesis that focused particularly on forests and rangelands we felt was really critical. And then finally, as I mentioned, we really felt it was important to provide this science foundation to build particular management responses for resilience and adaptation off of. So let me just start by a very simple definition of drought. And drought is essentially a period of uncharacteristically dry weather for a given location. And the reason that this is an important sort of starting point is that in some cases, places that are experiencing drought for another place in the United States, that might be a substantial amount of rainfall. So it's very context dependent, is that a system that typically receives a lot of rainfall can actually experience a drought, have ecological effects, have hydrological effects at a level of rainfall where in some parts of the country that would be a flood or a tremendous amount of rain. So it has to be in context of the given location. And so the bottom line here is that droughts occur everywhere, although some of the very dramatic and large-scale and obvious responses have occurred recently in Texas and the Mountain West in California. droughts also occur in the eastern United States as well. And it appears that over the last several decades, droughts have been increasing in severity and frequency both in the west and in the east. So droughts are a nationwide phenomenon. They're not just relegated to what's going on in the west, although those effects are often most dramatic and most obvious. And in fact, if you look at what's going on right now, this is a fairly recent update from the U.S. Drought Monitor. There are exceptional droughts or extreme droughts occurring both in the western United States and the eastern United States right now. So let me also just give a little distinction about drought types, because I think this helps set the context for some of the discussions that will come on later. Often what we think about in terms of drought is meteorological drought, and that's essentially driven by variation in precipitation amount, but it's also the water balance. So temperature has an important role in determining how much of that precipitation is evaporated off, either by vegetation use or by direct evaporation. Now, hydrologic drought is essentially how the ecosystem processes the amount of precipitation, or the water balance. So you can have a hydrologic drought that may be worse or less in some places, depending on what the water demand is and how the vegetation responds to that meteorological input. And then the final drought type is ecological drought, and that's essentially impacts. So that is how the vegetation, whether it be trees or rangeland vegetation, responds to the meteorological drought. So all these drought types are important, and we'll talk about a few of them in the coming presentations. I also want to point out that drought is more than just a normally low rainfall. It is lower rainfall, that is important, but it's also less snow. It's also changing in the dryness or the humidity of the air. It's in the length of dry spells, and it's also related to temperature. And higher temperatures during drought, which are certainly have been occurring or like to occur in the future, the context of the hot drought, all of these things interact with rainfall to either to typically exacerbate the impacts of a given rainfall or drought regime. So we know that with climate change, we have a fairly certain or more certain projections of temperature. So even if we don't know what's going to happen with precipitation, just warming temperature and the same precipitation regimes will increase drought stress. So a real question then is, how will drought regimes change in the future? As I mentioned, we have an expectation that droughts will become more frequent and more severe. And we get that from changes in what we've observed in the historical climate record, but also projections of what might happen into the future in terms of precipitation and temperature regimes. Unfortunately, one of the real challenges for climate change models is accurately or consistently projecting how precipitation is going to change in the future, so timing, but also where it's going to change in the future, so location. And as you can see in this graph, there are some places where the model agrees that precipitation change, in this case a decrease in precipitation in the red and the orange. There's some consistent projections in the southwestern United States in most seasons, but in a lot of the time there's some real uncertainty, especially in the middle part of the country. There is some uncertainty, and it does challenge a little bit our ability to project exactly where and exactly when drought might occur in the future, with a few exceptions. As I said, there seems to be some convergence around the southwestern United States as an area where precipitation deficits are likely to continue and get worse in the future. What's a little bit more consistent, though, is this idea of the change in the maximum number of consecutive dry days. So when it is dry, it's dry longer. And here there's a lot more consistency in what the models predict in terms of longer periods without rainfall, an increase in the number of consecutive dry days. So there may be some uncertainty in terms of the timing of the absolute amount of precipitation changes on a seasonal or annual basis. there is some convergence in the projections of when it's dry, it's drier for a lot longer period. Combine that with elevated temperatures, the idea of drought being an increasingly significant challenge and impact forest and rangelands more significantly in the future seems to be a reasonable projection. So, using this as a context of where we've been in terms of the changes and the impacts of drought, projecting in the future, I encourage you, if you want more details about how these might impact the variety of topics addressed in the assessment, hydrologic impacts, fire impacts, forest vegetation, biogeochemistry, details are in the reports, which I'd be happy to share. Some of these will be discussed further in today's presentations as well. So some of the key messages that I would like to just sort of close with is that drought is now affecting all ecosystems, and it could get worse in the future. The changes are most obvious in the west, but impacts in the eastern forest are occurring as well. They occur through a slower process of mortality of drought sensitive species and a slow decline of forests. So longer term, but impact still the same in the west, or in the east as in the west. The impacts are both immediate and long-lasting. The immediate ones are these big wildfires and insect outbreaks that have killed acres and acres of vegetation, but there's also more long-lasting effects where drought-tolerant species are favored and plants are under stress and grow less and reduce carbon storage. And as a result, there are some shifts in habitat as drier sites become less receptive to species that require more water. And they're taken over either by invasive species or by more drought-tolerant native species. So the impacts are quick in some cases, especially with some of the indirect effects that impact disturbance regimes, but also slow as the system responds to this chronic stress on the plants and ecosystem processes. So the real key is how to manage to increase resilience and resistance. And of course, one of the things that we know about both forests and rangelands is that they already have some inherent resilience and resistance to disturbance or to drought already, or they wouldn't be here because droughts have occurred, throughout time. The key is, though, are we reaching a point in the stress or disturbance regimes that are going beyond the ability to resist or be resilient to these systems, and that seems to be the case. So there is a strong need to manage to increase resilience and resistance. So there will be some challenges for the future, and I think we need to recognize these, and the research is not over, and the recognition that the learning process and monitoring needs to continue. And the toughest one is the detection. Where is drought going to happen and how can we detect it? Some of the uncertainties we're projecting future precipitation make this kind of difficult. Being able to detect anything less than massive forest die-off from satellite imagery can be kind of tough in forest systems because they don't necessarily give a signal that can be detected with some remote sensing. So predicting where it's going to happen and detecting areas under drought stress is a challenge. While we know a lot about how it will impact forest and rangelands, we don't know everything. There are some key uncertainties that we identified in some of the papers that I discussed further or earlier. And then finally, managing for drought. What can we do to make forests and rangelands more resilient? And I think that is the purpose of this initiative and the upcoming workshops over the next year. Thank you.
Thank you, Jim. Appreciate those comments. A couple of things going on in the chat room that we're noticing. There seems to be an issue with those of you that wanted to call in and listen over the phone. That PIN number does not seem to be working, but we're working on that. The other question that people are having, and I failed to mention this at the beginning of the webinar, this is all being recorded, all the PowerPoint presentations, the slides, all that will be available at a fairly short date, probably by the end of this week, in several formats. It'll be on a YouTube channel, but also available on our forestrywebinars.net site. So we apologize for some of the technical difficulties for those calling in on phones. I know that many of you prefer that format, but those of you that can hear me, if you wouldn't mind just pulling up and trying to use your computer audio, that should work as well. So with that, we'll go ahead and move on to our next presentation. And at this time, our next presentation on drought, forests and water resources by Charles Luce and Jim Bose. Charles will be presenting here, and Charles' presentation, Charles is a research hydrologist with the Rocky Mountain Research Station in Boise, Idaho. He has an undergraduate degree in forest management and a master's in forest hydrology from the University of Washington. His PhD is in civil engineering from Utah State University, and his research addresses ecological interactions with physical hydrological processes in forests and streams and the effects of disturbance and climate change on those processes. So, Charles, take it away.
Thanks, Bill. The reason that drought and water resources and forests are brought up together often is how much of our water in the country originates in national forest systems. About 10% in the Mississippi, around a quarter of the Missouri and Ohio systems, about a third of the Columbia River, and half or more in the Colorado San Joaquin systems. So we're big sources for a good chunk of the country in terms of water. So what we do as drought time rolls around becomes an important factor. In particular, there are a lot of questions about how our trees use water, and there's questions about forest management for water yield purposes specifically. In addition, given that the context of this kickoff is about drought planning, the permitting that we do relating to water users who are requiring permits for diversions or reservoirs or grazing on public lands interact with us. So there's a fun connection or nexus there between state laws, federal laws, and natural hydrologic laws that has to be reconciled together. And again, another piece there, these three, the Permitting Endangered Species Act, I sort of touch on at the end. The questions about forest management and water yield will be the bulk of this presentation. But given the planning context of this, talk about the rest of these things. As Jim mentioned, drought happens both east and west. In the east, in fact, if we look back in paleoclimatic times, there have been some rather significant and long droughts that have happened in the past, and nobody's positing any reasons why they should not potentially happen again. Of course, very rare millennial timescale type things. In the west, there are these significant droughts that have been going on now. There's, of course, the straight up precipitation drought that has occurred in California. But another kind of drought that is particularly affecting the West strongly because of the mountain environments is, as warming progresses, something called a snow drought, where warmer temperatures are making the precipitation that falls come as rain, which happens during the winter seasons, and then there's less water available during the summer months when the farmers and other folks need it. And you can see from across this map, if you look at the gradient, Oregon, Washington with the lower elevation ranges are seeing very significant declines in snow here on April 1st, 2015, as opposed to what's going on here further east where the elevations are higher. When we talk about drought and trees and stream flow all together, we can take a look at this fairly simple equation about the water cycle. And the upshot here is if we have precipitation as our main input, if we just take that out of the equation, just look at this side, if we lose precipitation, the stream flow, the evapotranspiration, and the storage, the amount of storage in the soil and bedrock need to decline. So we see less water in the streams, we see less water available for the trees, that's the ET, and a decline in the soil storage as well. And so vegetation is an important component here, and there's a trade-off between what happens for the stream and what happens for the ET as well. The classic story on how vegetation might affect stream runoff and evapotranspiration is taken here from the Fool Creek experiment. It was about a 5 square kilometer watershed in Colorado Rockies. There have been many other related experiments at Coweta, Fresno, in California, and of course the Wagon Wheel Gap study in Colorado as well. But this is a very nice picture of it. We see after the harvest, here in the dashed line, quite a bit more water, and that water comes a bit earlier. We can take a look at that also at larger scales. So that was a 5 square kilometer watershed. We had an opportunity because of long-term USGS gauging in the Boise River to look at a similar thing with 2,000 square kilometer basins. And sure enough, there, after burning down 45% of the basin, there were about 50,000 acre feet per year more available, which is about 5% more water than the average annual in there. And as we saw in that previous graph as well, most of this water came earlier, so in the months of May, April, March, and so on. A little bit more in August and September, and that's helpful for the farmers. All of this earlier stuff is not so helpful for them. So it's important context to realize what these trade-offs in water yield versus evapotranspiration mean for the timing of the runoff that we see. In addition, our long-term research, I'm pulling up a lot of studies here from our history because in part just to show that we've been learning about this for quite a while. If we look at the amount of increase in water yield from the experiments here on this axis as compared to what the mean annual precipitation is on the bottom axis, wet places over here on the right see quite a bit of response. Dry places and dry years show very little response. So trying to do something like removing trees in order to increase water yields may not do so much for our drought years. People have asked about thinning effects as well. One of those thinning experiments in Fool Creek that was published in the early 1940s showed nearly no response there. Later experiments here in Coweta and Fresno. What's interesting about those is, one, to see that there's a topographic aspect to it. There are also soil effects, slope effects, how steep the slope is. All of these things play into how much more water you get out of it. But if we look at the bottom axis here, which is reduction in forest cover in percent, so we're looking at more thinning on the left end versus clear cutting on the right hand end, we're looking at these lines not all coming into 0, 0, but actually beginning to hit the zero axis here about 10 to 20%. So light thins do very little for the water resources side of the equation. One reason we understand from that, looking at this Trundle 87 study, is that when we thin trees, the trees that are left behind use more of the water. So the amount of water used per unit leaf area left on the ground is higher. So the trees left behind can take up that water, grow faster. And one reason that this graph is important besides that is it shows that water for trees, the trees will use that. We can get resilience in our forests through the thinning even if we don't get additional water yield. So important to keep those two goals in mind and as separate items. Related, not so much treatment, but effect to thinning is mountain pine beetle. So we've seen quite a bit of thinning of our forests through various insect changes. This study was in British Columbia, and each number here shows the amount of evapotranspiration measured from the stands over the course of the 4 years following the beetle attack. The bottom one had a lighter beetle attack, and you can see that across both of these there's no trend. What the indication there is that and very similar studies that have been done in Colorado, but without quite so compelling set of graphs, shows essentially the same story, that the mountain pine beetle did not change our water yield from those basins. Related idea here, and again related to the soils and slopes and things like that, is that different trees use different amounts of water. This is from the east, where there's a huge biodiversity in contrast to many places in the west, although California has a pretty diverse set of stands as well. But if you look at the different species across here of tree, some of these use water more carefully than others do. And it depends a lot on their structure. The upshot of this is that we might get some non-intuitive outcomes in the short term and in the long term, and it requires some thought. So for example, from some Ips beetle kills in Arizona, there were post-mortality flow declines instead of increases. There was a temporary species shift, in fact, life form shift to grasses that took up any rainfall during the summer months very rapidly, evapotranspired that, and moved on. That eventually recovered. The story in the east with woolly adelgid, there was riparian hemlock die-off with an initial reduction in evapotranspiration, and that was then replaced with hardwoods with a higher evapotranspiration rate in the long term. So worth understanding those ecological relationships between species, and recognizing in this also the value of biodiversity. So large-scale drought-related die-off, say through insects or just straight up with the trees dying, is probably less likely when you have diverse stands. And so there's some potential there to buffer hydrologic swings. So as opposed to what we saw in the Boise, where we managed over the course of 10 years, and actually we burned a lot more of it since, to burn a very large fraction of the basin. Perhaps with biodiversity and something less happening that will buffer some of those ups and downs. If we have consistently increasing drought, that might favor dry species that accept dry conditions in the long run, and maybe that'll create drought resilience and low water use forests over time of its own accord, as long as we promote the biodiversity that allows the kinds of trees that adapt to the specific kinds of drought that are happening in that place to prosper, exist, and then prosper. So just to head towards finishing up here, with respect to permitting, there's a few things. Drought happens, and when it does, somebody along the line will declare an emergency and expect some responses rapidly. And that will affect our permittees. It might affect us directly as well, but more likely it'll affect permittees working with diversions, cattle, what have you, who have water rights to use drawn from Forest Service lands. And because we permit them, we have some responsibility for what consequences there might be to those. So, for example, if we have reservoir expansion requests for people preparing for changing drought conditions, those are going to have some consequences as well. Well drilling for cattle as well. If someone says, hey, this particular rancher needs to cut off use of water supply on this creek at the moment, and they need to move somewhere else, that has to go through our range conservation program. There's a lot that can be done ahead of time, working together to clarify which of these will work and which of these, in a particular circumstance, may not. Again, it's the conjunction between the federal and national laws is tough enough, but when we tie into this, for example, the idea that reservoirs are pretty helpful in the circumstance of snow drought, i.e. they help retain water that would have been retained as snow, but delay it up in the mountains for a longer time. They're not going to help that much with precipitation-driven droughts unless they're very big and can carry water over from one water year to the next. For the most part, reservoir expansion outside the context of snow droughts is not going to be all that helpful. So we have to keep all these ideas in mind in terms of what's helping build resilience versus not. With respect to information, the question is, can we help the states with their drought detection and planning? I was in a meeting last week for several western states trying to develop drought plans. And one of the things they kept bringing up is that the Forest Service is a big blank spot on the map. And enigmatic and inscrutable work well for wizards, but it's probably not such a good thing for public agencies. So what can we do to help them receive information? Of course, the question is there, can we operate our water storage and distribution systems more efficiently if we had better data from the National Forests? And the answer to that, people have done research on that question. It's an unequivocal yes. Some of our water systems with mountain snowpacks are the most predictable in the world. And it's because we have some information on the snowpacks. If we had more, we could do better. So what is the Forest Service role in providing or encouraging that information? That's very complicated. And as an interagency and across state versus federal government's question, but in terms of drought planning, a very worthwhile question to start answering. So for some summary points, forest harvest and thinning are going to be an unreliable source for water during drought. We understand enough about trying to augment water yield through forestry that we know we're not going to get a lot from that. But on the other hand, we also understand from that that thinning can contribute to resilience within the forest that's there. The ecological biodiversity understands, so promoting biodiversity can help buffer effects on forests, and they buffer effects to water yields. And just the fundamental bottom line that we understand, to play well with others, it's important to be prepared. And there's a lot of science that can contribute to those questions as well. That's all I had, Bill.
Thank you, Charles. I appreciate that. It looks like you've spurred a few questions, too, which will be great for our discussion time in a few minutes. But moving on, our next presentation set will involve two speakers. And Matt and Jessica will be speaking on drought issues and management challenges in forest and rangeland vegetation. So Matt Reeves is a research ecologist with the Rocky Mountain Research Station in Missoula. He received his bachelor's degree in range management, master's degree in environmental resources, and his PhD in remote sensing and ecological modeling of rangeland and agricultural environments. Matt specializes in applying remote sensing and modeling to characterize ecological dynamics of rangelands. His research follows four basic themes, including climate change, vegetation dynamics, anthropogenic disturbance, and decision support tools such as digital state and transition simulation models for improved management efficacy. And following him, Dr. Jessica Holofsky, a research ecologist with the University of Washington, is affiliated with the U.S. Forest Service Pacific Northwest Research Station. Her research interests include fire and disturbance ecology, vegetation dynamics, and climate change, specifically ecosystem impacts and adaptation. Jessica is currently working on several climate change science and adaptation projects in the western United States. Great. So Matt and Jessica, looking forward to your presentation.
Yeah, thanks everyone. Thank you, Bill. I want to mention something briefly. During this time, my computer is rebooted 3 times since this started, so if it happens to go out, I do have my phone ready to go, and then also the slides on a separate computer that's offline. So buckle your seatbelts. This could get a little bumpy for the time being. As Bill mentioned, we're going to talk about the drought issues and management challenges in both forests and rangeland environments. First, a couple of reminders. Drought is not uncommon in the arid West. I think most of us that are resource professionals understand that. And drought is also increasing in frequency with respect to more recent history. We don't know as much about the 5, 10, 20,000 year time horizons as we'd like to, but certainly with respect to recency, drought is increasing. And as Thoreau and Taylor in their drought paper in 1999 in Journal of Range Management had pointed out, it's an inevitable part of normal climatic fluctuation and part of our overall management scheme. And for those of you in the indemnity business or involved with USDA programs aimed at that, you know that it's among the most costly natural disasters that we face as a country and certainly as a land management agency. Looking at the effects on vegetation, again, most of us are resource professionals, so we'll take a 70,000 foot view of what happens during drought. First, vegetation production tends to decrease. I don't know about you, but during the summer, if I don't water my lawn, it gets brown, it doesn't produce as much, and certainly will die eventually. And we see that in wildlands as well. Plant mortality can increase, and that opens up more bare ground. So plant cover is reduced. And as the bare ground increases, more soil is exposed to rainfall events, and that can be significant for erosion. All these together indicate that habitat for wildlife will probably be reduced. Now, a very important point. We've heard a lot about fires and drought. Fires may increase in drought or maybe not. So let me spend a little bit of time with this question. On the X, you should see a black graph here with a red line. And on the X is fire return interval in years. The dots represent individual rangeland habitat types across the United States. On the Y is annual production in pounds per acre. What we see is those systems that tend to have very long fire return intervals tend to be on the low end of the productivity spectrum. And the key is that during periods of drought or in areas that have very low rainfall, we don't see a lot of fuel to propagate the fire. Well, let's take a look at across the U.S., at least with respect to non-forest systems. How does this play out? Well, if we focus on the green line, which is the upper part of this graph, where the X represents years since from 2000 to 2015. On the Y is our 1 hour herbaceous fuel load. So this is the herbaceous component of the fuel bed in pounds per acre. The green is an area in southeastern Montana. You can see that the peak was in 2011. We had a very abnormally high rainfall, created a high fuel load condition relative to average. Then in 2012, southeastern Montana experienced a significant drought, like much of the western U.S. That spurred one of the largest fires in history there, the Ash Creek Fire, greater than 350,000 acres. So in this case, the drought combined with a fuel buildup from a very wet year produced this condition. Let's contrast that with the southwestern United States represented in the blue and yellow lines. 2005 was in fact a very wet year and was also a very significant fire year in the southwest. So here it was the wet years that produced the fuel for fires. So I just say that drought does not always mean greater fire potential. It just depends on the system we're talking about from a national perspective. Some other effects. Some pests and weeds may increase as mineral soil is made more abundant. Some of these propagules from the weeds enhance their ability to reproduce. Forage value and carrying capacity for wildlife and native ungulates can decrease. We've seen this graph, and what it represents is the Cumulative Drought Severity Index. And what it represents is areas of the United States that have undergone very significant cumulated drought. And you can see that in the circles and also the points there. The second graph on the right represents two time periods for both the West and the East, the 1960 to 86 period and the 1987 to 2013 period. Notice the West. We see a very large increase in the number of red bars, and that's bad. That means we've increased the categories of severe and extreme quite significantly during the period of 87 to 2013. In extreme droughts, trees are increasingly susceptible to attack, and we see here in this case an attack by pathogens and pests. We see this pinyon dieback in New Mexico, plus or minus 90% in these images here. So drought causes the trees to become stressed, and this makes them more susceptible to attack by these pests and pathogens. We also see other places like this ash juniper dieback in the left. This was credited to Rob Jackson, and it's actually ash juniper at Colorado Bend State Park. And then another image of pine dieback, a different species of pine. This is not pinyon in this case. So just more evidence suggesting the impacts of drought. Finally, I want to conclude this miniature session with a thought-provoking idea, I hope, and that is what I have represented here is accumulated USDA drought monitor from 2000 to 2015. So we just summed this 52 weeks in a year, so 52 periods times 15 years, 16 years, you get an idea of what's going on here. And what it shows us very clearly is from 2000, the darker, the redder tones indicate areas that have undergone relatively more drought. So this kind of serves to point out the importance of monitoring, because what we think, we tend to think our area is the hardest hit, but in fact it might be our neighbor that needs the most help. And so using a variety of drought metrics, not just one like the USDA Drought Monitor, but a variety, I think going forward is going to be very critical to managing our resources and also helping us prioritize where and how we adapt. And with that, I'll turn it over to Jessica.
Okay, Jessica, you may need to press your talk button at the top of the screen there.
Okay, can you hear me now?
We can hear you, but there's quite a bit of echo, so you might want to turn down your computer speakers.
Is that better?
I believe so, yes.
Okay. Okay, thank you, Matt. So I'm going to talk about how the information Jim and Matt shared can be applied in vegetation management and basically how we can respond to drought. But I first wanted to point out that drought is not the only stressor in these ecosystems, and it doesn't act in isolation. And in a changing climate, it will be likely that the interactions among stressors, or we can also call that stress complexes, will be the major drivers of vegetation change. And so this example is for lodgepole pine forests in the west. And in lodgepole pine systems, drought will likely interact with fire and insects to lead to mortality, lead to subsequent fires and changes in species composition, including exotics. So it's important to consider the interaction among stressors when thinking about planning for and responding to drought. So I'm going to give several examples of adaptation strategies that were developed for drought in a series of science management climate change adaptation workshops that were conducted in national forests and national parks over the last few years. And these are the types of strategies that will be further developed in the series of drought workshops that will follow this kickoff that Cindy West mentioned. So for forest vegetation, a primary strategy to increase forest resilience to drought is to reduce stand density. And Charlie already covered this. Stand density can be reduced with thinning, prescribed fire, and also in some cases wildland fire. And with thinning prescriptions, managers may want to consider greater reductions in density than they used in the past. Another thing to consider would be including larger openings in thinning prescriptions and potentially planting seedlings in the openings to create seed sources for native drought-tolerant species. But in general, planning and promoting drought-tolerant species could help increase resilience to drought. So tree improvement programs could be used to ensure availability of drought-tolerant tree species and genotypes. And also increasing diversity is another general hedge-your-bet strategy that could help increase resilience to drought. So age class and structural diversity can be increased across the landscape through regeneration, harvest, thinning, prescribed fire, and also wildland fire use. So in rangeland vegetation, resilience to drought can be increased by maintaining the integrity of native plant communities. So this can be done through active restoration, and also key is to reduce the abundance and prevent establishment of invasive species. So for invasive species, implementing early detection, rapid response is also brought up. Rangeland managers can also do things like promote weed-free seed, make sure that weed-free policies are included in any planning documents, and those policies are incorporated in projects. And also you can expand weed-free feed lists to include additional non-native species. Large disturbances are likely to become more frequent in rangeland ecosystems, and so planning ahead for these events, whether they're droughts or fires, can help minimize negative outcomes. So for example, managers can maintain a seed inventory with high-quality seed for a range of species, particularly species that may do well in the future under hotter and drier conditions. And lastly, developing grazing plans that are flexible in the event of a drought can also help to ensure resilience of rangeland vegetation. So for all vegetation types, we know that drought and other stressors cross boundaries. And this is going to force agencies to coordinate and work across boundaries. And with increasing cross-boundary disturbances like drought, agencies can do things like align budgets and priorities, increase communication and coordination, and also work across boundaries to ensure continued public safety and also access to our national forests and public lands. And then monitoring is also going to be very critical to increase understanding of when and where vegetation is changing, and also what type of treatments will be effective to meet our management goals. So there are many aspects of resource management that can incorporate both climate change and drought vulnerability assessments, and also adaptation strategies and tactics. And in national forest planning, these include planning and assessment, NEPA analysis, project design, and also monitoring. So we're hoping to explore different applications of drought information and adaptation strategies in these different areas in the upcoming workshops, and figuring out more specifically where this information can be applied. And I wanted to conclude with a few thoughts on how the Forest Service as an agency can move the needle in preparing for and responding to drought. And I think that proactive rather than reactive approaches to prepare for drought will be critical. And finally, as I described a few slides ago, I think agencies will need to work together and pool resources and information to prepare and to respond to drought more effectively. And with that, I'll turn it back over to Bill. Thank you.
Thank you, Jessica. I'm running a little behind schedule, but I know John Stanturf with his quick talk will get us back on track, right, John? Dr. John Stanturf is a senior scientist and former project leader with the Center for Forest Disturbance Science, Southern Research Station. He is a soil scientist by training and specializes in restoration ecology. His current research focuses on climate change adaptation. Welcome, John.
Thanks,
Mike
Bill.
is yours.
Thank you. I like to start my presentations by giving the conclusions so that you know where I'm coming from and also where I'm going. And if you don't like it, then you can go to sleep. But basically, I'm going to try to make 3 points today. And some of these points have already been made, but I think they bear repeating. Drought and heat-related stresses are ubiquitous across the country, and it's probably going to worsen under climate warming. Well, I'm hearing a lot of feedback. Are you all hearing that?
Yeah, it looks like I need to mute. Let's see, probably need to mute Jessica's mic if she doesn't mind.
The second point is it's not simply a matter of drought equaling more frequent or more severe fire, but it is likely that drought and heat-related stresses will worsen an already challenging wildfire situation. And then finally,
John, hang on just a second. Okay, there we go.
Got it? Okay.
Sorry about that.
Finally, a warming and drying climate is going to challenge our ability to maintain carbon storage in our forests. So let me just get the technology going here. So this rather complicated slide is really just an overview and a roadmap of where I'm going to go. It's to give you some background and context. The diagram illustrates some of the connections and feedbacks between fire and climate. And in terms of climate, you can read in there drought and extreme heat episodes. But climate controls fuel amounts, fuel loading through vegetation. And it also controls flammability or fuel condition through weather. The connection to ignition, third leg of the stool there in the fire arena, is lightning. And that's a relatively minor contribution in North America, where we folks provide an awful lot of ignition sources, and we don't have to worry about ignitions being in short supply. With temperature increases, drought and low fuel moistures may become more likely in those summer dry climates that several of the speakers have already talked about that are primarily out west. And that will occur even with higher precipitation. As has already been pointed out, it's not just about how much precipitation arrives in a year, but when it comes and in what form, basically between snow and rain. So drought interacts with other controls on forest productivity, including topography and weather, to affect fire severity and intensity. Decreased overstory leaf areas as a result either of drought-induced or intentional thinning could increase water available for understory plants, which could include invasives, leading to higher intensity surface fires. In all these cases, the vegetation, the carbon stored on the site, is going to respond to fire frequency. Other stressors could increase. For example, higher temperatures accelerating bark beetle life cycles could significantly increase fine fuels immediately and fire hazards for years following outbreak. So just to back up a little bit and talk about fire frequency. Now, this is not area burn. This is the numbers of fires. This is a reconstruction that Rich Goyette and others have done from about pre-colonial or colonial times through 1850. So historically, fire frequency in the continental U.S. looks very different from the popular conceptions of where wildfires occur, if you only get your information from CNN and other news sources like that. This reconstruction of fire frequency from colonial times through the middle of the 19th century indicates most frequent fires are in the South, the Southwest, the Prairie States, and the Mediterranean climate region of the West Coast. Now, climate change projections suggest that fire hazard is going to increase, basically in those areas where fire occurrence has historically been highest. It's going to increase in most seasons and regions of the continental U.S., but the largest increases will be in the Southwest, the Rocky Mountain region, the northern Great Plains, the Southeast, and the Pacific Coast, caused by higher temperatures and increased evapotranspiration. Fire occurrence, though, is only part of the story. Land use change has fragmented landscapes, especially in the east, and that's reduced the continuity of fuels, which has an effect on the size of fires in the area burned. Better access and early attack in the eastern states reduces the likelihood of very large fires, so that the area burned is really quite a different picture. And this is wildfire activity by county for almost a 20-year period. The area burned in wildfires has been dominated by the western states in recent years and in interior Alaska. This map shows on a county basis the frequency of fires 300 acres or greater in size, and it's the big fires that attract all the attention. Notice that even over in Hawaii, in the tropical areas, there's been some big fires. Those, of course, were ignited by lava flows. The occurrence of big fires, some that have become the so-called megafires, are what's eating up the fire budget and eating up the agency budget. The specter of drought and a hotter, drier climate increasing the frequency of megafires is a great concern. So we've heard a lot about the evidence of drought already. Just let me provide a little different perspective. There's good evidence from backcasting from climate models that we've been in the midst of a relatively wet period in the long-term climate cycle. Evidence from tree ring reconstructions suggests that at least locally there have been periods of megadroughts of such severity and duration that they exceed anything that's been experienced by modern society. This graph from one area in northwest New Mexico goes back over 2,000 years and shows a cyclic pattern of wetter and drier periods lasting for hundreds of years. Areas above the line are higher precipitation areas, and below the line, drier periods. A critical point, I think, from this data is that megadroughts have occurred before any possibility of man-caused climate change. From that, we can infer that droughts will occur, and warmer, drier climate will increase the likelihood of drought and possibly cause longer droughts with more severe consequences. So, as some of the other speakers have mentioned, and I'll ask again, is it just a southwestern phenomenon? And the answer is no. Drought's a complex phenomenon, and there are several ways to define it, as Jim Bowes already talked about. From our perspective of forests and wildfires, we need to think about heat-induced tree mortality as well as extended meteorological drought. This map that you've already seen in a little different form, it shows the cumulative effects of drought over a recent almost 30-year period. And it shows that drought's not just a western problem. You can see drought effects in the lake states and in the southeast as well. Those blue dots are where there's documented heat-induced tree mortality. In other studies, a composite of 10 global climate models indicates that summer, that is June to August, water balance deficits are increasing in much of the west, except in areas of the southwest where monsoon precipitation and in portions of the Pacific Northwest. There's a genuine concern about late growing season moisture stress increasing in many species, even in northeastern forests, that typically you don't think of drought there. An important point in the Northeast and Midwest is that we're getting more rainfall, but more of the precipitation is coming in torrential rain events that don't necessarily provide moisture at the right time for plants and are not able to be stored in soil. It's become flood events. So how can we relate extreme drought events, extreme events such as droughts, altered precipitation patterns, and a changing mean climate toward a warmer and drier world with wildfire severity and area burned? Here's one representation that tries to put all the factors together. Climate change on the left there and variability may increase drought frequency, drought severity and duration, and directly affecting area burned. Indirect effects through insect disturbances and tree mortality may change landscape patterns and species composition. Putting it into a regional context on the right there, that incorporates fire exclusion and fuel accumulation effects and other factors affecting fire behavior, feeding into changes in landscape patterns, species composition, and area burned. So as I said in the beginning and others have said, drought does not automatically mean more fire. It depends very much on the context. Another point about drought and fire is that too often we only think of the effects of drought on fire, but there's an important feedback of fire to drought, that the particles emitted from fires affect the atmosphere by scattering and absorbing solar radiation. This affects precipitation and cloud formation regionally, such that fires in one region can enhance or prolong droughts in another region. And this has already been shown in modern times for the Yellowstone fires and for other fires. Now, it's important to remember that we're not talking about fires causing drought, but fires affecting the drought. So some of the other challenges need to be mentioned before we leave this big picture of the fire and drought interactions. Throughout the presentation, I've made some allusions to land use change. Without going into any detail, I'll just mention a difficulty you all are already aware of, I'm sure, and that's the increasing incursion of people and structures into the wildlands, the so-called wildland-urban interface, or WUI. Reducing historically high fuel loads and maintaining manageable levels involves the use of prescribed fire. But in addition to the difficulties of using fire in the WUI, managing smoke is a big challenge in using prescribed fire. Prescribed fire has got to be part of a long-term effort to manage hazardous fuels. There's many aspects of smoke management, and I can only mention just briefly a couple. Public acceptance is a big one, but health and transportation hazards are others, And increasingly, other regulations such as regional air quality are constraining the use of prescribed fire. Here in the South, where I am, smoke management is one of the significant constraints on the ability to manage fuels. Another constraint on the horizon that I want to bring up is the need to store carbon in forest ecosystems. To date, the contribution of carbon stored in public forests has been part of the U.S. policy response to international agreements, including the Paris Climate Change Agreement that's just about to go into effect. Reducing fuels means reducing carbon. So far, Forest Service carbon reporting has focused on operations, but in the future we may be required to report on the carbon effects of forest management. And then finally, as we all already know, it's only a small percentage of the fires that account for more than 90% of suppression costs. So if big fires or mega fires increase in frequency and severity as a result of increased drought, already stretched resources, including trained people, are likely to be overwhelmed in the future. Let me bring it down now to from the big picture level to some sort of regional looks at the fire-drought interaction. Let me start in the Southwest, where we've already heard about pinyon juniper systems that already start off as water limited, and was mentioned earlier in Matt and Jessica's presentation. A severe fire is sometimes preceded by a wet year. So the wet year in a water limited system provides more fuel than normal or than average, and that fuel then burns. Recent diebacks in the system caused by high temperatures and low precipitation and stressed trees just set them up for its infestation. More severe droughts likely with heightened fire risk, and large-scale severe fires inhibit regeneration, and without management that's likely to lead to shifts in vegetation. In the Sierra Nevada mountains, particularly lower elevation subject to the hot, dry summers, a history of fire exclusion, native and non-native pathogens, and protracted drought is likely to lead to more large fires. Somewhat offsetting this is the lowered vigor due to ozone effects at higher elevations, but also you have the situation where once you've burned everything up, you're going to be looking at some differences in vegetation types. Moving to the east, the interior lodgepole pine forests, we've already heard a little bit about them, they're all pretty much approaching maturity, and thus they're quite vulnerable to bark beetle outbreaks. Warmer temperatures have affected fire potential by accelerating pest reproduction and morbidity and mortality of the pines. This increases the fine fuels immediately and also the crown fire potential. More severe drought makes fire more likely in these systems, makes large fires more likely. And far north in south central and interior Alaska, large crown fires and spruce beetle outbreaks are more likely under higher temperatures, again for the same reasons. The probable scenario here is a conversion to less flammable deciduous species such as birch and willow that will be maintained in the landscape over long periods. Coming east, in the northeastern deciduous forests that mostly we think are unaffected by fire, paleo as well as historic evidence suggests that disturbances, including drought and fire, were more common before European settlement. Since then, the spatial continuity and scale of disturbances has become much smaller than in the West. But here, wind disturbance is common, and like Hurricane Matthew that we're expecting to hit in East Coast in the next few days, or tornadoes throughout the region. And these interact with other disturbances. The predictions are for longer fire season in local areas, such as conifer-dominated forest on outwash sands in the Lake States, one of those areas that showed to have cumulative drought effects. You also have the same kind of systems on Long Island and in New Jersey in the Pine Barrens. In the southeastern region, where I'm from, there are more fires here than anywhere else in the U.S., but they tend to be small and mostly extinguished quickly. Prescribed fire is used extensively, to the tune of several million acres annually, to control fuel loads and for other management objectives. As I've already stated, smoke management poses a major constraint on the use of prescribed fire. But the South's not immune to megafires or to drought. Climate predictions are for an extension of the wildfire season and tighter windows for prescribed burning within prescription. So basically, we're going to have a harder time managing fire effectively. Some of the management options for reducing drought and fire hazardous fuels will meet some of the needs to maintain fuel loads at safe levels, but these options have already been discussed, so I'm not going to go into any detail. I just want to point out again that adapting to drought and reducing fuel loads by manipulating vegetation may lower the carbon storage potential of the forest. Whether managing fuels by multiple low-intensity prescribed fires produces less emissions over rotation than one or more high-intensity wildfires, that's an open question that may have different answers in different regions or forest types. Certainly any answer would be incomplete unless the full carbon costs of fire suppression are factored into the analysis. And this is one of the knowledge gaps that I think needs to be addressed. Some of the other knowledge gaps in our understanding of drought and fire, for one thing, our understanding of drought effects at the stand level is based mostly on extrapolating the effects of drought on individual trees. We don't have a lot of truly stand level information where competition, invasive plants, and pest interactions as well as fire are incorporated. One result of this is that we know only a little about the delayed mortality caused by heat, short periods of water deficit during the growing season, and long duration drought. While species shifts may result from drought and fire, to what extent can active management, including reforestation, overcome this? And is there the overall uncertainty of what the future holds in store in terms of climate change? What and where will we experience novel climatic conditions? What novel combinations will we face of altered drought frequency, intensity, and seasonality? And will we face novel fire regimes as well as novel fire behavior because of species shifts and invasive species? Some preliminary answers can come from modeling studies, but they won't be definitive. Enhanced experimentation at landscape and regional scales and more intensive monitoring will be needed. So in conclusion, I just want to make some main points back to pretty much what I said at the beginning. Increased droughts are likely and may be exacerbated by climate change, and all the forests in the nation are subject to drought and heat-related effects to some extent. In addition to the increased likelihood of wildfires under drought and a warmer and drier climate, wildfires feed back into the climate system by emitting particles that can intensify or prolong drought in other regions. And finally, we need to be more aware of the interactions of a warming and drying climate with increased fire hazards on our ability to manage forests so as to maintain carbon storage to mitigate climate change effects. And that's all I've got.
Thank you, John. Next up this afternoon will be Dr. Dave Peterson. David L. Peterson is a senior research biologist with the U.S. Forest Service Pacific Northwest Research Station, where his research focuses on climate change effects and fire science. He is currently working on climate change assessments and adaptation in national forests in the western U.S. Dr. Peterson, good to hear from you, and look forward to your presentation.
Okay, thank you, Bill. We're going to change pace a little bit here in talking about recreation and ecosystem services, and that might seem like a little bit of an outlier compared to the other topics that we've been talking about. But I hope to show you some of the connections and show you that it really is a very relevant aspect of how we're looking at the issue of drought. This is just a brief outline for how I will go about this presentation. First of all, some context, interactions amongst various resource sectors, projections of future conditions, and then some potential solutions and directions for the future. Just waiting for the slide to come up on my screen here.
I can move them through for you, Dave, if you're having problems on your end.
Yeah, it shows that it's advanced, but I'm not seeing it on the screen.
The one we're viewing right now is recreation is a growing economic driver.
Okay, that just came up for me. So one of the biggest rationale for including recreation is it's a huge economic driver throughout most of the United States. And we tend to think of, to a certain extent about some of our extractive resources, timber, mining, and so forth. But if we look at just the numbers, for example, in the Intermountain region of the U.S. Forest Service, recreation generates over $1 billion a year. And we have 19 million visitors in national forests, 24 million national parks in that area. So that's a lot of people, and that's a lot of cash flow moving through the system. So the Old West has really changed. And I think to a certain extent we're just now coming to grips with the new environmental values and resource demands for resources. And it's also a growing management issue here with respect to ecosystem services, because the President issued this memorandum just about a year ago that institutionalizes policies relative to ecosystem services. So now in forest planning, assessments, and so forth, we're required to consider ecosystem services. And I just mentioned this issue of carbon management down below because it's so relevant to the other things that have been discussed today and very relevant to drought as well. Just a brief overview of what we expect the effects will be on different aspects of recreation. So if we look at cold weather recreation, now this is a huge enterprise, particularly in the western U.S. For example, in the Intermountain region of the Forest Service alone, there are 21 ski resorts in this area. And the effects of a lower snowpack, of course, will be to uniformly cause a shorter recreation season. Folks will have to maybe move to higher elevations, and some of our ski resorts may see some difficulty in the future if they don't modify operations. Now, as for warm weather, this is a big winner. Lower snowpack means we have a longer recreation season, more time for things like hiking and camping, especially in those shoulder seasons of the fall and spring. But the thing with this issue is that it creates some challenges in terms of managing facilities and opportunities which might not otherwise be available under current weather conditions. There's a number of other things that are relevant in recreation, hunting, fishing, water use, and things like special products, cone collection, huckleberries, and so forth. Again, we'll have a longer season in which these kinds of activities can occur, although in some cases the low stream flows that Charlie Luce talked about earlier could have some significantly negative effects on fishing. Some of our other resources, the effects are maybe neutral, although if we do get more wildfire, as John Stantorp has been discussing, and we have a lot of smoke in the area, and we may also have less access to some of our resources. In addition to drought, there's the issue of variable water supply, flooding, other kinds of issues. We've certainly seen a number of significant safety events that have occurred over the last several years relative to flooding and recreation. There could be some effects on fish habitat. And probably the biggest effect here is when we have things like road washouts, bridge washouts, and so forth, because that totally reduces access to recreation resources. And that can affect a big portion of the public that like to use public forests. Again, I'm getting a little bit of delay here in the slides showing up, so I'll just wait a few seconds, Bill. Okay, it came up. So let's take a quick look at the current management context for recreation. This is a huge enterprise for national forests and other public land agencies because millions of visitors use those lands. It's managed actively in some cases and passively in other cases, such as in wilderness areas. the maintenance or recreation corridors, those important roads for getting out to the forest, are critical. And currently the Forest Service uses the travel analysis process to identify what a sustainable road system may actually be. Now it's important to note that the vast majority of recreation is less than a day. In fact, the average visit to a national forest is only 6 hours. So that is the user group that we're trying to connect with here. Unfortunately, current recreation practice is relatively inflexible. And so we have things fairly well structured by seasons. We depend very heavily on a summer, typically, seasonal workforce. And the amount of funding that goes into recreation is relatively low compared to the enormous economic value of recreation. There is some interaction with other resources such as in engineering, roads and infrastructure, but not that much with other resource areas in the management sector. For ecosystem services, this is kind of a new topic for our resource managers, and it's just now starting to be addressed explicitly. And in the future, I think we'll see this as a major consideration in planning. It covers lots of different resources, many of which do have existing guidance and best management plans. But how this moves forward, I think, is open to question. Whether or not it's treated as a discrete topic or within each individual resource area, I think will be developed in the next few years. So the year 2014-15, the winter without snow as we call it, in the Pacific West and Northwestern continental United States was a real eye-opener for us. This was a region of the country where we had snowpacks of 5 to 10% of the average. And so things like skiing, snowmobiling, and so forth took a real hit. What we learned from that winter without snow was that recreationists are very adaptable. They found snow to a certain extent. They went to higher elevations, places that had snow, or they just started their summer recreation activities. However, our federal agencies weren't so adaptable because of some of the structures and processes that I just mentioned. However, what we found is our recreation managers totally understand how climate and weather affect recreation, and that they have some great ideas for how they can adapt to this in the future. Again, just waiting for the slide to come up. So now a little bit of talk about solutions. And there are some very good pathways for building resilience. First of all, we can start working with future scenarios of if, when, and where drought might occur. We can manage proactively, as was mentioned earlier, not reactively, so we can start building this resilience not just into our ecosystems, but into the organizations that manage recreation and ecosystem services, and also to incorporate this idea of drought thinking, that this might be something that's going to happen more often in the future. We have lots of examples. First of all, we probably need to take a look at the capacity of our existing recreation sites, what that is now and how it might change in the future. Developing flexibility in the workforce is extremely important if we're going to indeed have this bigger period of summer recreation. Take a look at our road and trail closures and how that meshes with recreation demand. And we're already seeing this development of a multi-season approach at ski resorts throughout the West. Just waiting for the slide. Yeah, sorry about this, folks. There seems to be a little bit of a lag, at least on my connection here for the slides coming up.
Yeah, we've got it. We've got it here at the central base, Dave, so you can probably begin anytime.
still not working here. Rather than waste too much time,
yeah, we're on the slide right now, which is building resilient ecosystem services. Some examples.
Yeah, mine's not coming up, so
that's too bad. Well, that's probably fortunate, Dave, since we're running out of time a little bit.
Conclusion section here.
Okay.
Yep. I've got the conclusion slide up now, so let's just finish this up. We feel that recreationists in general are adaptable and that they will kind of go with the flow here no matter what happens in the future. Unfortunately, our agencies are not that flexible, and we have some challenges for responding to drought. There are some options. I mentioned a few of them. There are many more that we can explore. The same is true for ecosystem services, but at least for the near term, those options will probably be very specific to individual landscapes and local values. So let's just tie it up there, Bill, and move forward.
Great. Thank you, Dave. I apologize for that technology. They were showing up almost immediately when you clicked out here, so it must be that time delay across country, right? Anyway, great summary. Ecosystem and recreation services, thank you very much. Last but not least, on with us to talk a little bit about the business of sustainability is Dr. Sarah Baker, registered professional engineer, is a program specialist with a programmatic focus for the Office of Sustainability and Climate Change Operations. She received a bachelor's degree in civil engineering and a master's degree in engineering water resources from the University of Texas at Austin. She worked for the USGS Water Resources Division for 2 years before joining the Forest Service in 1989, where she has worked at all levels of the National Forest System, from the district office to the Washington office, and in regions 2, 10, and 3. Her work to promote sustainable operations in the agency started in 2007. And Sarah, thank you for being patient, and we'll look to have you wrap things up, and then we'll move into a discussion section.
Great, thank you. And I've had enough coffee, I may be able to help wrap it up quickly. We've all heard about now how we manage our resources and services for sustainability. I work in operations, so I want to talk about how we manage our own actions to promote sustainability of our agency and of our human systems and our own ecosystems. I named this talk Walking the Talk of Conservation Ethics. And I realize that walking the talk is cliche, but in this case I think it's apropos, because we're the ones who actually walk the forests and grasslands. So what I'd like to do is discuss a little bit about how we show up, and then talk about how we understand and share things like our climate change impacts on our infrastructure, our own consumption, and the mandates related to that, and how we manage our infrastructure impacts and how that affects our resource management. Then I'd like to share a little bit of the next steps in the OSCC operations around water savings. When we talk about showing up, we've learned years ago some very important lessons. One is that we can't survive without partners and supportive publics. And the other is that if our partners and public believe that we're saying do as we say and not as we do, they quickly become our adversaries. So we need to think about this as we're working on the land. Our offices are a large part of our public face, along with our recreation sites that Dave mentioned. Would we be hearing about it if we were watering massive lawns in the middle of a drought in New Mexico or Colorado? You bet we would. So we need to ask ourselves, are we showing up as concerned about the water resources we manage? As we manage our forests, are we concerned enough about our greenhouse gas emissions to limit our travel and to drive as efficiently as possible when necessary? Are we energy efficient? Are we reducing waste? Are we recycling? And this isn't just about appearances. If we're hoping to conserve our natural resources, we have to be conservationists. So that's what we need to think about as we're showing up on the land. I mentioned the greenhouse gas emissions. We want to reduce our human-caused warming, so we need to reduce our greenhouse gas emissions. This agency has been measuring and reporting on greenhouse gas emissions since 2010. It's important for us to know where we can have the biggest impacts as we try to become more efficient. So our three biggest areas of greenhouse gas emissions are our mobile fleet emissions, our building energy use, and our employee commuting, which we probably don't have a lot of control over. But we're mandated to reduce all three scopes of greenhouse gas. This is while we're conserving water. So I'd like to bring this back to our impacts on our infrastructure. We've talked about the impacts to some of the infrastructure that Dave mentioned during recreation, but we really have to think about what we would lose during fire and flooding. We have buildings, 40,000 buildings, that we could easily lose those as we have in the past. We can lose vehicles, and recreation sites, and roads, but also the smaller pieces like the wildlife fences, the trails, power lines, water systems, wastewater treatment systems, and then the big bridges and dams. Some of these are weakened by fire and destroyed by post-fire flooding and ash flows. So without these infrastructure pieces, we can't meet our mission. That's the key to this. I want to talk specifically about water. We manage 4,800 drinking water systems across the agency. This doesn't include the water that we pay for from utilities. This is just the ones we manage. These supply water to administrative sites and recreation sites, and they all have to meet the Safe Drinking Water Act. As we look at what happens when we have drought and the water table drops, or when we have flooding that floods out our water systems, we look at wellhead damage, or we look at well contamination. That makes it impossible for us to meet the Safe Drinking Water Act, and that, by the way, has personal liability associated with it, so it's pretty important. Then we also look at the added costs of deepening our wells, repairing them, or in some cases closing them. And while we're looking at these costs, our utilities are going up because the public utilities are facing the same situations we are. And then consumption of this water, we talked about being aware of our own consumption. The federal government's the largest single energy user in the United States. We also consume a lot of water. We're looking at 131 billion gallons a year by the federal government for operations. For the Forest Service, this is in the range of 526 million gallons a year, a $2 million plus annual cost for water. And when we're talking about this, we're talking about what we use in our own facilities and our recreation sites, and not what we use for providing services other than those. So this is really internal operations, and when we think about what that means, every person in the United States uses about 36,000 gallons of water in their home for indoor use, not including swimming pools. The cost in this depends on where you are. In Albuquerque, I only pay $90 a year for my water, which is really inexpensive. But when we think about water use, we are not including things like the average U.S. diet, having embedded water 10 times that of what we use for our houses indoors. The point here is that water, like carbon, is embedded in everything we do. And the other point is that quite often we're not seeing the real cost of reducing water, of our water savings. If you've been through a hurricane, I grew up in New Orleans, you know what the true value of clean drinking water is. It's incredibly important. We also have mandates for reducing our water use. We have to reduce our water consumption intensity, that is gallons per gross square foot, by 36% by FY25. The mandates have other requirements like installing water meters, and we're supposed to use that data to actually improve our water consumption and management. But one of the things I want to share with you is my favorite part of the executive order, Planning for Federal Sustainability in the Next Decade, and that's the policy section, the first section. It states that we will continue to drive national greenhouse gas reductions and support preparations for the impacts of climate change. I love that. That's really inspiring. Of course, I'm easily inspired by executive orders. Looking at the water systems, though, we need to look at a bigger thing than just our particular water systems. We need to look at the systems of water. When we're reducing water, we're not just reducing the water and saving the watershed. I'm sorry, I'm laughing because my pictures moved around. We're looking at a bigger system. Besides the watersheds that we protect, if we reduce our water use from the faucet, We're reducing the energy it takes to treat that water and the energy it takes to pump that water, and then the energy it takes to treat the wastewater. We're also reducing the chemicals used to the water treatment and the wastewater treatment. And if we reduce the amount of wastewater to treat, we reduce the possibility of that water being released into our watersheds. So this really supports our research management goals. When we talk about infrastructure management and the impact it has on our resource management, one of the big pieces that's really obvious, I think, is our huge deferred maintenance backlog. As Dave mentioned, we don't have enough funding for our rec sites or our infrastructure. We have right now a $92 million backlog of deferred maintenance just for our drinking water systems. That's a $5.2 billion infrastructure deferred maintenance backlog. As we look at the impacts of climate change, making these facilities making the facilities more vulnerable to climate change, that means that our deferred maintenance goes up on both our drinking water systems and the rest of our infrastructure. The result of that is that we have less funding for our infrastructure and less infrastructure to support the resource management needs. The next steps I want to share very quickly about our Office of Sustainability and Climate Change Operations for water conservation is that we are introducing the corporate priority action item in 2017 around water assessment and tools for efficiencies and reductions. So you'll notice that spells out water. We're going to be looking at water system leaks and outdoor water use across the agency. That alone could account for about half of the potable water used by the agency. As we go over the next 3 years, we expect to reduce up to 40% of our potable water consumption. That would more than meet our mandate of a 36% reduction. The steps for doing that would be to compare the water use to the water estimates, assess what we're using outdoors, and then prioritize the sites we're going to work on. Then we'll be working on these sites and identifying ways to really help with the resources for the field. Our challenges, and these are challenges for the future, but challenges for all of us as we face climate change impacts. How do we help others connect these dots? How do we help others figure out how to show up as responsible for the resources that we're managing? And how do we move these discussions that we're having from these few people on this webinar to the bigger part of the agency? The field doesn't always have time to consider how we do things differently, but they're the ones that have to do it. So we have to help them. And then how do we make our own infrastructure resilient in the face of all of this, all these impacts? What do we do to help prioritize this work? We have vulnerability assessments, adaptation plans all over the place. How do we tie them into our facilities' master planning efforts? So those are the big challenges for us here on this webinar and across the agency. And I wanted to end this with a little quote from our founder. I was very inspired recently by going to Gray Towers and was impressed with Gifford's insight into the future. So this is from Gifford Pinchot. The vast possibilities of our great future will become realities only if we make ourselves responsible for that future. I love that. And that's it for me. How about that for going fast?
Thanks, Sarah. And that was actually a perfect wrap-up. I commend the group that organized this webinar because I think your presentation really brought us back home. So fantastic. Great news. Okay. While we're getting ready for the short bit of discussion we've got for our time here, we have about 15 minutes tops to go through some questions that I've been tallying on the side, and then if you have some on your own as well, go ahead and type them in. I'm going to attempt to send out the information that so that you can get CFEs, take the quiz. I'm going to put it here in the chat window as well. If those of you that want to get offline or go and take that quiz, hopefully it'll redirect you back to the main session. And let's see if that works for folks. Let me know. I know when there's so many people coming into the server, it on occasion will slow things down over there. But I'm going to go ahead and see if we can get offline here. So let's get some of these questions rolling. There was a few that came in just about everybody's presentation. First, a quick one, Jim Vose, if you can recall, there was a question on what CDSI stands for on a map in your presentation. I apologize that that didn't get answered during your presentation, but if you're online and can answer that question, that'd be great.
Yeah, sure. I apologize for not explaining that. Fortunately, some of the other presenters did, but I believe it's a Cumulative Drought Severity Index. So it's a way to essentially quantify one of the many metrics used to quantify the severity of a drought. Okay, great. This one, I'm going to bounce around a little bit to get everybody involved here. Is the Forest Service reaching out and sharing data with others to be proactive on drought management? If no, what has been the barrier preventing this? I believe this may have been for Charles.
Right. For the most part, the Forest Service doesn't collect that much in the way of climate data. Some at the weather stations, and those are reported just through the Weather Service. The bigger question is the why. I just don't think it's been considered part of the mission, or there's lack of funding. I'm not entirely sure, but those are a couple that have come up before. NRCS collects quite a bit of data off of Forest Service lands, though, so that's the kind of the primary source, and then the RAWS system, I think, is distributed through the regional climate centers. So there's a few different sources of data. I don't know how well it's coordinated, and certainly we're pretty sparse on Forest Service lands.
Okay. There's a question here. Let's see. Joe James from South Carolina asked fairly early on if we have processes to convert fire-damaged trees into viable bioproducts, with whom might we collaborate with at the U.S. Forest Service? So I'll throw that one out to all of you to see if anybody has a response for Joe over in South Carolina. Nobody's going to try to tackle that one?
Bill, this is Cindy. There are a number of places to work with the Forest Service on that challenge. Contacting in terms of what's going on the ground, working with state and private organizations. That would be within our state and private forestry program. And so if folks want to know locally where to go to, contact Steve Kane at the U.S. Forest Service, who is the director for cooperative forestry that oversees that program.
Okay, great. That's Steve Kane with the USDA Forest Service, Cindy, and if you can type that in the chat window, or if I get a minute, I can track his information down. But quite a bit going on, I think, both in state and private, as well as even R&D, I think. Okay. This is from Salim. Salim asks, are climate data used in the development of Forest Service UMPs? I don't know if that was BMPs or UMPs, but I'll again throw that out to the speakers to see who would like to take that one. Oh, unit management plans. Thank you, Salim. And it looks like Anthony answered that. The answer is yes, the planning rule makes climate change as one of the stressors to consider when developing a plan. Okay, back to Jim Vose. What is the impact of fracturing, employing large volumes of non-reusable water, on climate change?
I'm sorry, I didn't have my microphone on. I honestly don't know the answer to that. I assume that by fracturing, the question is also fracking, so essentially redistributing water, from surface sources down to deeper sources. I have no idea what the influence of that would be on climate change. I suspect that locally it could have an impact on water resources. Whether that's a significant enough event to actually impact climate change, I don't know. I doubt it, but I don't know the answer to that. Maybe Charlie has some insight.
Okay.
Yeah, I don't. Specifically, the water input isn't going to do that, but of course it allows access to more greenhouse gas producing emissions.
I think so. Operating ARB.
Okay, there's a couple of comments just to let folks know. John, somebody said thank you for bringing up the fire and drought correlations. Let's see, there was a question about thinning, and I don't remember exactly where this came in. Thinning is a key. Where did your 29% come from? I don't know if that's, was that vegetation management possibly with Jessica and Matt? So thinking about, yeah, thinning is a key. Where did your 29% come from? So if anybody can claim that one, that'd be great.
Yeah, I think that must have been on Matt's presentation, that slide that he showed, percent thinning. Because I didn't put any numbers on mine.
Okay.
Yeah, this is Matt Reeves here. I don't have anything about, I didn't have anything about thinning, at least not that I recall. So I'm drawing a blank on that.
Okay. All right. Well, in the interest of time, we'll move on. So Amber asks, does any of your research use the soil data from Web Soil Survey? So that would probably be open to any and all of you using any of the data from Web Soil Survey.
Yeah, this is John. I certainly use it, but not in this context.
I would echo that. Use it extensively, but not necessarily from the perspective of drought. Okay. And Julian asks, can you briefly note how you guys are working with federal partners outside of USDA, for example, NOAA, DOI, BIA, BLM to address drought, especially in the West? Any comments from our Western partners there, either in the Rocky Mountain or PNW?
Bill, this is Cindy again, and I have some folks in here who might be able to provide some information.
So yes, hi, this is Toral Patel Waynand. On the drought synthesis that we pulled together that Jim Lois mentioned earlier on, we had a number of the federal agencies that were involved, as well as state partners, as well as other stakeholders. And I know that our climate hubs are working with a number of folks, both on public and private lands. And Dave Peterson and others in the PNW area are also working in various areas, particularly on adaptation issues and determining vulnerability issues. And Dave, could you speak a little bit about the partners that we're working with on the federal agency and the state agency side? I don't know if Randy Johnson is on the line, but he might be able to speak to some of the partners we have out west. So do we lose Dave?
This is Dave. Can you hear me, Bill?
Yes, you're on.
Okay. So in assessments that we've done with national forests in the western U.S., we've included National Park Service, sometimes Bureau of Land Management, U.S. Fish and Wildlife Service, and other federal partners, as well as state partners, tribal partners, and NGOs in addressing these kinds of issues, typically for vegetation and water and wildlife. So we do try to make those connections as best we can, and I think it's really critical because obviously for an issue like drought and water and so forth, these are all lands issues, so we really do have to have that sort of collaboration.
Just one other additional thing in terms of working with partners with regards to the California tree mortality issue and the 10 communities that have been impacted. We're working very closely with the Governor's Task Force and CAL FIRE and the other agencies to ensure that everything that can be done is being done, both from a restoration perspective and also from meeting the needs of the communities that have been impacted by drought. So there's a fair bit of work going on both on the science end, but also on the ground practical issues that national forests have to deal with.
Okay, thank you very much. One more quick question. Is there any indication of changes in winds as energy transfer in drier conditions? Higher wind speeds would tend to remove more water from a system in summer transportation and winter snow sublimation. So not sure if anybody can handle that one in about a minute or less.
Hi, this is Charlie. There are quite a few papers out on this idea called global stilling. With the way temperatures are changing, there's some reduced pressure gradients that are reducing the winds and reducing evapotranspiration.
Great, thanks. Very succinct answer. I've got 3 o'clock. I want to thank all of you that hung in there. I really appreciate the speakers staying mostly on time. I think we were able to go through all the presentations and had enough time for any questions that popped up. But look forward to the regional workshops and the results of those. So that's all the time we've got today. I will ask Cindy if she would like to say a word or two. Other than that, you should have gotten a link to take your quizzes if you want your continuing forestry education units. If not, please contact me at whubbard@uga.edu and we'll make sure you get your credits. Thanks again, everybody.
Thanks, Bill, for hosting and being a great moderator. Appreciate everyone's time today. Hope we have created some new thinking, give you some new information. Of course, ultimately, this makes sense where you are and what your situation is on the ground, and we will be moving down to do some sense making of that, to looking at where we can develop some strategies and tactics, learn some more about the implications on drought and important resources and the jobs we all have to do. So thanks again. Appreciate your time today.
Okay, thank you. Take care now. Bye-bye.